Okay, in this video, I'm going to go over determining the overall design requirements. In this particular case, we talked about two load conditions. One is the 1,200-pound clamping force, and then we're also going to consider the situation where somebody could apply an 80-pound load over on the handle, okay? So again, when we're doing these things, it's one thing to say them in words, but honestly, the more appropriate thing to do, or the thing that adds a little more definition, is to actually draw something like a free body diagram that really shows the loading situation. So here we have just I did a little drafting view and kind of printed out some profiles of the toggle clamp assembly. Now, in this particular case, this design, it's a bit complicated by the fact that this toggle clamp can actually actuate at a variety of angles. And technically, when we talk about these max loading conditions, especially for the second one, we really should consider at every possible configuration in which the load can be applied, because that will, depending upon the configuration, you'll get different loading in the different members, okay? But just to keep this one a little more straightforward, I'm going to just stick with it in the closed situation. And especially for the first design requirement, this is the 1,200-pound clamp force. All right, so that means that acting up here through the rubber tip, we can have 1,200 pounds acting up. All right, now again, that force comes about because you've locked down and you've compressed the clamp section a certain amount. There's a stiffness associated with the clamp section, and then that'll push back through the contact force, load onto the clamp. All right, and nothing needs to fail at that load. Okay. Theoretically, again, remember, the mechanism can hold an infinite load because it's gone over center, just a very slight amount, this 1 1/4 degrees. But that doesn't mean that there can't be a structural failure, that obviously it will no longer perform. Also, it could deform enough where the lock over clamp mechanism is not really over center anymore, right? And at which point it'll also unclamp, okay? But, and honestly, I should consider all those possible configurations, especially with regard to the tolerancing about whether or not there's enough play that, if there's enough play between, I can't see, enough play between the pins and the handle such that this can swing back or forth by about a degree or so, you might be in a situation where it doesn't really go over center, and the clamping mechanism, the over center clamping mechanism, doesn't really work properly. But anyway, so let's just go through a basic loading type of design requirement, the 1,200-pound force. So this is not quite sufficient yet, because obviously it's not in equilibrium. The clamp assembly is being held down here to some base through these two fasteners, okay? So really, technically, I should find the reaction forces, okay, to be complete. So you'll have some force resisting the 1,200 pounds acting at the fasteners. From looking at this, you can tell, the way these things always go is there's a net down force of 1,200 pounds acting through the two fasteners. That'll basically give you like 600 on each, and then there'll be a moment, the 1,200 acting through this point, that gives you a moment this way, so there has to be an additional couple applied to the fasteners to balance that out. So you'll probably get this one with the force acting down and this one pulling up. Okay? Okay, so let's label this BY, and we'll label this CY. And obviously the easy way to get this is through it's statically equilibrium. I mean, it's statically determinate, so we get this through just the equations of equilibrium, right? So if we do sum of moments around a point, let's say we do sum of moments around point B, that's obviously going to go to 0, and so this distance here, it's a little hard to see, is 6.88, and this moment arm distance here is 2 inches, so obviously I just get that off of the CAD. So sum of moments is 1200 times the 6.88, right? That would be a negative moment. And then we have a positive moment of the CY acting around its moment arm 2. And that equals 0. And then we can get from that CY is going to be 600 times the 6.88. And if we calculate that out, that becomes 4,130 pounds about. So this is 4,130. The direction is consistent to what I labeled here. And then we can do sum of forces in the y to get by, or in other words, by equals CY minus the 1200. Okay? And that is we get the through 1200 plus CY, yeah, it's plus 1200, right? Because they're both acting up. So this becomes 5,330 pounds. Now, both of these are acting on 2 bolts. Because remember, at point B, there's 2 fasteners coming in and out of the board, right? One's behind the other, and same with C. So actually this 5,000 pounds is actually about 26.5 on each bolt at B, and likewise this one is 2,065 at each bolt on point C. Okay, so I would probably take this, I would probably make it a little more cleaner and neater, but this now defines the one design requirement for the system. Okay, all the components have to stand this load. I can now go from this standpoint and figure out for this loading situation, what are the stresses in the arm? What are the stresses in the bracket? What are the stresses in the toggle arm, the handle? What are the loads or the stresses in the clamp link, okay? And the shear pins and all that sort of stuff, okay? But those are, we're going to talk about those being derived design requirements. Excuse me for kicking this thing, okay? But to do that, we have to document the top level design requirements. So that's the first one, all right? Now we also had a second one we wanted to consider, which was, do I have another piece of paper here? Yeah. Possibly somebody can apply 80 pounds of force on the handle. And again, this is why we want to be careful about how we define these things. Is the 80 pounds going to be here or here? Obviously, that'll have a difference on how the handle and the cross arms and all the other members are loaded up. So we need to define that, okay? So we might say, well, typically the 80 pounds, is going to be halfway through the handle, okay? So if we call this LH for length of the handle. This distance here should be LH on 2. All right? And, we decide that makes that assumption. And this is now 80 pounds. All right, so when we look at that, obviously in this situation, what's going to pick up that shear loading has to be an 80 pounds shearing on the bolts, okay? So a reasonable assumption would be that there's 4 bolts, so we get 20 pounds on each bolt, okay? But this should be 80 pounds of shear acting on the bolts. Now, we're going to also have a moment here, right? So we've got a big moment arm here. And, man, do I have enough dimensions on here? Boy, I guess I don't. I need to have some other dimensions. I really need to figure out this distance here. I'm going to have to go back to the CAD and figure out that distance. But anyway, there's that moment. And this really sets up an interesting situation. So if you think about it, you have, a tip force acting through here, and then again some reaction forces acting at the base. So if we think about this, we actually have a statically indeterminate problem. All right, and that makes it difficult because then, you could pose it as a design requirement that's statically determinate. But then to really check the loads acting through the different elements, you have to have a complete design and do a pretty heavy amount of iteration. But in this particular situation, I think we can kind of make an assumption that'll make our lives a little bit easier. Now, this 80-pound force, if you think about it, this is the force that someone's using to lock it over. Now, this can happen once the workpiece has been clamped or before the workpiece has been clamped. Obviously, that's a dynamics problem, but when the workpiece is clamped. Now, what really governs the clamped force that's acting here is, what is the workpiece that's being compressed, right? So one can argue that this is a little bit out of our control from a design standpoint, right? You can't determine what that force is until you know exactly what the workpiece is and what's being clamped. And there's no way you can do that because this has to work for a wide variety of specimens. So considering that, it's probably reasonable to say, well, look, is going to be when we have the 1,200-pound clamping force. Does that make sense? This is like a worst case situation. All right. And now when I do that, then you can see that, in fact, these forces can be determined. All right. So let's call this again BY and CY. I really need this distance to get the moment. Okay, so let's see if I can pick it off. I can. Usually I try to get this stuff ahead of time, but let's see if I can do this relatively quickly. My computer's been a little glitchy. Oh, I can do it probably right from... Let's go to drafting. Maybe you can pick it up right up in drafting. Because I already made a view that pretty much shows this. Huh? So let's put a dimension on here. Okay, dimension 2. Well, I can do the handle height. Where's my dimension thing? These won't be exact because of the angle, but maybe more. From here to here. Okay, so that's 3.94. I'm going to just write that on a piece of paper, and we'll come back to that. And then let's get this distance from here. Let's go from this point down to that center mark. Okay? And that's 3.94. 3.73 inches. Now I probably should get this. I guess I could do it this way. Can I pick it up from the edge? This way at least gets that moment arm correct. Okay, so this, if I do it this way, because of the 1 degree angle, right? So that's 7.67. All right. So let's go back to here. I think I got enough dimensions, right? So that's 7.67. So this distance here, the one that I need for the moment arm, right, is going to be the mean of these two. Let me get my calculator. Awkward pause. But I'll just do, again, sum of moments around point B, and then that'll give me CY, and then I can just do sum of forces, right? So, okay, that distance is going to be 7.67, 3.73. So this is 5.70 inches. And so the total moment arm from here, this is terrible dimensioning, from here to here is going to be the 5.7 plus this 3.83, which is 9.53 inches. Okay? All right. So from that, we can do, well, I probably should get another piece of paper. Let's get another piece of paper. Make it neater. So let's do sum of moments around point B equal to 0. So what do we have? We have the 80 pound acting through this 9.53 moment, and that's going to be a positive moment. So we got 80 pounds, and its moment arm is the 9.53. All right. Then we have the 1200, which is a negative moment, and it's still the same moment arms we had before, minus 1200, and its moment arm is a big number. That's the 6.88 to 0.8, and it's a negative moment. And then we have CY, which has the same moment arm of 2 before, so that is another positive moment. CY times 2, and that has to go to 0. So we get that CY equals 6.88 times 1200 minus 9.53 times 80 all over 2. And that becomes, excuse me a second while I do this. Still going to be dominated by that 1,200 pounds. That's the thing, right? 9.53 E times minus, drop a little bit, 2 divided. So that's 3,747 pounds. That's what's acting up at CY. So that's, if we compare that, right? That actually dropped a bit, right? CY has dropped a bit. It was 4,000 in the first case, and now it's 3,000 in this case. So loosen up those bolt forces. And then we can get sum of forces in the Y to get BY, right? So we have BY, it's negative, so I can bring it on the other side, equals CY plus 1,200, okay? And so that's going to be, oops, 4,946. Again, with the same, actually 47 if we round it. Again, that is over 2 bolts at points C and B, okay? But we can rank that, right? So this is going to be 3,750. I usually don't go beyond 3 significant digits, and then BY is going to be 4,950. All right? So again, I have 2 loading cases. I have to design for both, right? You can see there is a little bit of difference. With regard to the forces through the fasteners and the load plates down here, it looks like actually this requirement might be a little more stringent, but the upper handle is not loaded at all, whereas in this situation, the upper handle is loaded a bit more. The axial force in the bolts is dropped, but we also have this additional shear. So, you know, I don't know which will be the limiting case, but we have to design to both, okay? And for some reason, my ACES thing is loading up, but that's okay, because this is the end of